take care of this. I didn't fail again. We have a class of acids and bases. They're called amphoteric species, or amphiphilic. The amphoteric, what it means is it can act either as an acid or a base. And it depends on the mixture, how it behaves. And so first let's recognize amphoterics. There are a lot of species. Some of them you don't think of as being amphoteric, like ammonia. Ammonia, you wouldn't normally consider that as amphoteric. We normally think of ammonia as a weak base. It's a very common weak base here. It's stronger than, well, the bases table is inverted. The acid table, the top is here. The strongest acid is HClO4. So if HClO4 is a strong acid, that means its conjugate base must be extremely weak. And so the weakest base on this list is Cl4- or perchlorate ion. And then the weakest acid on this chart is methane. In fact, we don't even think of methane as being an acid, but if methane were to act as an acid, it would form methide. And therefore, methide goes to methide. Note the naming. Hydrogen goes to hydride, methane goes to methide. So that's nomenclature thing. But methide's the strongest. So the strongest is down here. So if we look at ammonia, I would rank ammonia as being weaker than cyanide. So cyanide's a stronger base. This is Bronsted. Cyanide's a very powerful Lewis base. Lewis bases we treat differently than Bronsted bases. So ammonia is weaker than cyanide, but it is stronger than this one. It's that one. Monohydrogen phosphate. And so that's where it ranks. However, ammonia is what we call an amphoteric species, and it can act as an acid. It's not a very good acid. When you look at its acid strength, it's weaker than water. And water, do you really consider that as much of an acid? No. And so ammonia is even weaker than water, and if ammonia were to lose a proton, it forms this one. What is this called? Amide, right? Methide, hydride, amide, ammonia. Or maybe ammoniide, but ammoniide is hasn't been used, and so people just call it amide. So there are some weird ones here that are amphoteric. Hydroxide is a weird one. Hydroxide is a powerful base, but it's also an exceptionally weak acid here. And so hydroxide can be amphoteric as well. And so there are a lot of species that occur on both sides. Phosphate does not, there's no proton to donate, so phosphate's only a base. But monohydrogen phosphate is both. Monohydrogen phosphate is an acid, and monohydrogen phosphate is a base. So it's both an acid and a base, so it's amphoteric. Now, how it behaves depends on what it's mixed with. And so what is it? Is it going to act as an acid or is it going to act as a base? Well, it depends on what you mix it with. So ammonia, is ammonia going to act as an acid or is ammonia going to act as a base? I don't know. I don't know because I don't know what I'm mixing it with. So for example, if I mixed ammonia with the base phosphate, and I think, okay, what I'm going to do is I'm going to mix ammonia and phosphate. That means ammonia is the acid, phosphate's the base, because phosphate can't be an acid. So we donate a proton to phosphate. What forms when we donate a proton to phosphate? What forms when we donate a proton to phosphate is monohydrogen phosphate. And so this is the zigzag method. I mentioned the zigzag method. Have you had a chance to look at the zigzag method before? So the zigzag method goes like this. If ammonia and phosphate react, I make the acid monohydrogen phosphate, and I compare the two acids. Which one's a stronger acid? Monohydrogen phosphate or ammonia? So this is what we call uphill thermodynamically. So if we go uphill thermodynamically, we don't want to do that. You know, in nature tends to go downhill, not uphill, right, for reactions. And so this is what we call an unfavorable. There's no driving force for this because we're going uphill here in the Chem 1A sense. And so ammonia is not going to act as an acid, but however, if I took ammonia and reacted it with the oxide, what forms? If I take ammonia and react it with oxide, then the conjugate acid of oxide is hydroxide. And when I compare the two acid strengths, this is going downhill, and so this zigzag works. And so ammonia can act as an acid as long as I react it with a base that's stronger than, what's this base called? Amide. So that's always going to be downhill. So what does ammonia react with when it wants to react as an acid? It reacts with, yeah, it's going to react with oxide, no problem. What's this one? Hydride, no problem, forms hydrogen, and methide. And so ammonia will react with those species as an acid. Otherwise, it should react as a base. Reacting as a base, then we want to go downhill. So ammonium and ammonia is a tie, but if we go dihydrogen phosphate, that's stronger than ammonium, and so that's going to result in downhill. H2S, this goes downhill. Carbonic acid, downhill, zigzag. And so you can see what it's going to react with as an acid, and you can see what it's going to react with as a base.
So if, for example, we're mixing ammonia and water, and in previous chapter we discussed that there's equal parts hydroxide as ammonium.
Yeah.
What would happen in that situation?
Okay, in that situation, that's very good. And then in fact, that's something I'm going to talk about here. What would happen if you mix it with water? Water is very interesting because water can go both ways. Usually there's a preference. So for hydroxide, the preference is a base. It's a much better base than it is an acid. In fact, it's such a bad acid, we don't even consider hydroxide as being very acidic.
What would you have to put in there?
To make hydroxide an acid?
Yeah.
Well, we use the zigzag method for that. And not too many things will make hydroxide act as an acid. What are two of them? Methide and hydride, that's it. If you have oxide, it's a tug of war. It's a tie, oxide versus oxide. No one's going to win the tug of war for the hydrogen ion. But if you have hydride versus oxide, hydride's going to win in this particular case. And so we can use the zigzag method, but it has to be something very powerful. Very powerful. So what do we do? Well, let me show you. I told you that monohydrogen phosphate is amphoteric, correct? It can act either as an acid here, or it could act as a base here. So which one is it going to act as? Well, we saw this in the previous problem. I think I was working on phosphoric acid here. Step 2. Step 2, step 3, monohydrogen phosphate, step 3. Step 3 here, you see I have monohydrogen phosphate here, and it can either act as an acid or base. And so what is it acting as in this equation here? It's acting as an acid, and then I have Ka here, so it's producing hydronium. But why didn't I have it react as a base? Actually, that's not the reason I did it. In this case, this is what you want to remember. The original problem is this will save you. The original problem is 3 molar phosphoric acid. And what else is there? Water. And so when we have 3 molar phosphoric acid, this is an acid solution. In an acid solution, we only look at Kas and Kw. Kw is a Ka. And so we ignore all the Kbs. And so monohydrogen phosphate has a Kb, dihydrogen phosphate has a Kb, phosphoric acid does not have a Kb. It can't be a base. Why did we ignore those Kbs? Did I tell you why we ignored the Kbs? I think I told you for amide, didn't I? Why am I ignoring the Kb? And so here I'm at dihydrogen phosphate, and I'm only looking at the Ka, but I completely ignored the Kb. Why? Okay, there are 2 levels of why. One level of why is don't do Kbs. If it's an acid solution, only do Kas. So that's a rule. If it's a base solution, it doesn't matter if you have an amphoteric species or not. You're only going to do Kb. You're going to ignore all the Kas. For a base solution, for acid solutions, ignore all the Kbs.
I mean, just in the questions, like, would it specifically ask to find Ka only?
No.
It's just inferred.
Yeah.
What are going to be like our range of considering like really basic or really acidic?
No, it doesn't matter. Even if it's weakly acidic, only Kas. It doesn't matter if it's strong or weak. If it's acid, Ka only. If it's base, Kb only. Do you know the reason why? Let me tell you the reason why. Let me insert this here. The reason why we're ignoring the Kb, let's go to monohydrogen phosphate, because I have some room here. Because monohydrogen phosphate has both a Ka, that is, when it collides with water, 2 things can happen. 1, it could lose a proton, or 2, it could gain a proton. And these collisions happen at random. And so there are definitely going to be collisions where HPO4, 2-, collides with the water molecule and gains a proton. If it gains a proton, it forms dihydrogen phosphate and hydroxide. And so it's colliding with water, and there are 2 outcomes. When monohydrogen phosphate collides with water, outcome 1, it generates hydronium and phosphate. Outcome 2, it generates hydroxide and dihydrogen. In other words, it can either gain a proton or it could lose a proton. Kb, it's gaining a proton. This is Kb. But why did I ignore? Why was this reaction ignored?
Maybe because monohydrogen phosphate is a stronger acid than water.
Stronger or weaker, I don't care. I want to, even if it's weak, I'm not going to ignore it. It's like if you have a weak child, do you ignore it? You know, that's a weak child, I'm going to ignore it. I'm just going to focus on the stronger child. You know, do you guys follow the Big Bear Bald Eagles? If you follow Big Bear, I've been watching the Big Bear Bald Eagles, and I notice how they feed. You know, it's like the strongest of the chicks, eaglets or whatever they call them, got all the food. And then I was thinking, oh, number 3, chick number 3 is being neglected. I didn't watch the whole thing, but I noticed that. Wow. And then this big storm passed through Big Bear, and they got like 3 feet of snow. And then unfortunately, I think it was chick number 3 ended up dying. But we shouldn't ignore chick number 3. We should feed chick number 3, right? It shouldn't be ignored. I think that just chick number 3 just didn't have enough calories to last through the storm, maybe. That's from the, I could be totally wrong, you know.
You're shaming, but
Yeah, I'm thinking, why? I was thinking, feed chick number 3, come on. Don't give all the food to chick number 1. Come on. That's what I was thinking. You know, that's what I was screaming into the thing, because you're ignoring. Come on, they're ignoring that one. That one's the weakest. That one was the last one to hatch. But anyway, it was pretty sad because I was thinking we were going to have 3 bald eagles. But they have a live webcam, and so if you want to waste hours watching that, you can watch that, which I've done. I've wasted lots of time watching it. But, you know, it's pretty interesting. Anyway, going back to this, why am I ignoring? I don't want to ignore the weak ones. I want to do the weak and the strong. I don't want to be biased in that sense, or, you know, like that. You know, otherwise I'd have to yell at myself. Why am I ignoring this? Any other?
Does KA take into account KB through the...
No, KA is a different collision. So we have 2 collisions going on. And we have lots of water, so we're going to have both. Both of these collisions are happening. I can't stop KB. KB is going to happen regardless of whether I'm there or not. You know, I can't say, okay, like I'd like to say to the eagle, you know, feed the other chick, but they're not going to pay any attention to me. You know, just like the monohydrogen phosphate won't pay any attention to me. Both of these prefer the reverse reaction. So whether it's KB or KA, they're both going to, this one's going to strong base, hydroxide. This one's going to strong acid. So both of them actually prefer the reverse direction because the driving force just isn't there.
Is it based on the concentration that we're adding that makes us...
It could be, you know, sometimes, but the concentration of monohydrogen phosphate is the same and the concentration of water is the same. You know, the concentration of water is close to 55.5 molar, and the concentration of these, you know, it's monohydrogen phosphate in the same beaker. You're just saying, and sometimes the monohydrogen phosphate collides with water to produce hydroxide, sometimes it collides with water to produce hydronium. And the answer to this is, why was the reaction ignored? It was not ignored. We already did it. We already did it. How did we already do it? I don't remember doing this ice table. You know, there was no additional step for this ice table. And this is how we already did it. How we already did it is, this describes the equilibrium between monohydrogen phosphate and dihydrogen phosphate in terms of hydroxide, in terms of pOH. We already did it because we already did this equilibrium. Where did we see the equilibrium between dihydrogen phosphate and monohydrogen phosphate? We saw that in the previous step. We already did it here. Here's the equilibrium between dihydrogen phosphate and monohydrogen phosphate. The only difference is we did it in terms of pH, not pOH. But you have to remember, if pH goes up or down, pOH does the opposite. And so they're tied together. And so it doesn't matter if I'm looking at this in pH or pOH, they're completely tied together by pKW. And so pOH and pH are tied together by pKW because the pH plus the pOH has to equal pKW, which is 14.00. And so this is what I mean by we already did it. And so you can save yourself some headache. The KBs are all going to be like this for an acid solution. We've already answered it in terms of pH. And so it would be redundant. We'd be going in circles. So this would be another death loop, Chem 1B death loop. If you started doing this, you're going to get a whole bunch of, and there are sharp students. There are sharp students who go, well, you know, I can't ignore KB, can I? And so then they started adding KBs in addition to the KAs, and they go on for like 5 pages. You know? And they don't really get an answer. And so you can save yourself some headache. For acid solutions, only do the KAs. The KBs would be redundant. You've already done them. You know. However, what if we don't have the previous step? You know, what if I just had monohydrogen phosphate alone? If I had monohydrogen phosphate alone, that's a totally different question because I had not done it yet. And so for amphoterics, an example of that would be like say I had sodium monohydrogen phosphate. If I had sodium monohydrogen phosphate, then I cannot ignore either. Because if HPO4 2- reacts with water, I could form H3O plus and phosphate. Or if it reacts with water, I could form hydroxide and H2PO4 minus. And so this is my Ka collision, this is my Kb collision. But there's nothing else in here. And so is there a step before this step that I already solved the equilibrium? No, this is the start. And so these are not redundant. So we have to do both. Well, if we do both, then there is a common species. And the common species is HPO4 2-, but there's one other common species, and the common species is hydronium and hydroxide. Hydronium and hydroxide have to approach a balance called Kw. So we have to do Ka, Kb, and Kw. Not both. We must do all of the equilibria. We'll just say all equilibria. Ka, Kb, and Kw. Not only that, we must do this simultaneously. Do you remember the math I showed you for two simultaneous equilibria? Yeah? Yeah, the system of equations. I did the mass proton balance. Let me show you one other one. What did I do? I'm going to post these too. I was supposed to show you this one first. Before showing you the second one, because I didn't complete the table of the second one because I had already done it. I'm showing you a second method for solving simultaneous here. I just emailed it to myself, but I don't know. It's going to take a long time to come. Well, I'll check back on this later. On the one hand, this simultaneous equilibrium is more difficult because we have 3 ice tables. On the other hand, this simultaneous equilibrium is easier because 2 of these ice tables involve HPO4 2-. And so let me make a long story short. The long story short is somebody went through this and solved it simultaneously and then came up with a simple equation for this. The simple equation it breaks down into is kind of weird. The pH of this solution is going to equal the pKa for the conjugate here, HPO4 2 minus, plus the pKa, I mean, for the amphoteric here, HPO4 2 minus, plus the pKa for the conjugate, H2PO4 minus, divided by 2. This is, we come up with this equation assuming SA works. And the initial concentration is not so diluted, it's pure water. I'm sorry? Yeah, pKa. This is quantitative. Qualitative, we do it this way. So if I want to determine the pH, I can solve it simultaneously, but somebody figured it out. Save us a lot of math. That it can be simplified to this algebraic equation. Qualitatively, we do this, where we ignore one kind of versus the other. We don't really ignore it, but we just say, we look at the Ka for HPO4 2 minus, and we compare it with the Kb for HPO4 2 minus. And so the question is how do they compare? If they're roughly equal, then we're going to produce equal amounts of hydronium and hydroxide, so we should get a pH close to 7. If the Ka for HPO4 2 minus is greater than the Kb, then the pH should be less than 7. And if the Kb is greater than the Ka, we produce more hydroxide than hydronium, and the pH should be greater than 7. So qualitatively, we can determine, is it going to be more acidic or more basic, or what is it? And so we're going to compare it. And so if we compare the Ka for HPO4 2 minus, let's look at what is the Ka for HPO4 2 minus. I had that earlier. Actually, it's off the chart there. It's 2.2 times 10 to the minus 13. So this is 2.2 times 10 to the minus 13. And then we need the Kb for HPO4 2 minus. The Kb for H2PO4 minus is not on the chart. How am I going to get the Kb for HPO4 2 minus? Not on the chart.
Don't you just take like the opposite, like the opposite?
Yeah, the opposite. We don't call it the opposite. We call it the. This is Kb, so I need the Kw, and I'm going to use the conjugate base or the conjugate acid of HPO4 2 minus. I'm going to use the conjugate acid. What is the conjugate acid of HPO4 2 minus? Yes, H2PO4 minus. That's correct. And so Kw is 1.0 times 10 to the negative 14, and then Ka for H2PO4 minus is 6.33 times 10 to the minus 5. Is that correct? 6.33 times 10 to the minus 5, I think. Oh, no, it's not. Is it minus 5 or minus 8? Can't read that. Negative 8? Okay, thank you. 6.33 times 10 to the negative 8. All right, so... 6.23. Oh, 6.23. Okay. I should be wearing glasses, but I don't wear them. So I do 1 times 10 to the negative 14 divided by 6.23 times 10 to the negative 8. Well, that's didn't work. 1 times 10 to the negative 14 divided by 6.23 times 10 to the negative 8. So I got a KB of 1.605 times 10 to the negative 7. So which one is bigger? KB is a lot bigger, a lot bigger. So we expect this to be a basic solution overall. If I want to figure out what the pH is for this, then I could use this simultaneous method. I might as well do that. Let's figure out what the pH is. I know it's basic. The pH is going to equal the pKa. The pKa is the negative log of the Ka. The Ka was 2.2 times 10 to the negative 13 plus the negative log of H2. So P, that was 6.23 times 10 to the negative 8. And so the negative log of 2.2 times 10 to the negative 13. So 2.2 times 10 to the negative 13. Take the log of that, base 10. And I get 12.657. I'm allowed 2 sig figs, but I'm going to carry an extra. And then the negative log of 6.23 times 10 to the negative 8. 6.23 times 10 to the negative 8. 7.205. Divided by 2. So I'm going to sum these up and divide it by 2. .93. 1. So to the correct number of sig figs, it should be 9.93 pH. So when we have an amphoteric species are a headache because there's both a Ka and Kb. But fortunately, somebody did all the math. And so what we're going to use is what's called an engineering equation. Have you heard of engineering equations? Engineering equations is just plug in the variables and it's going to spit out the answer. We're not going to derive the equation. We're not going to try to figure it out. And in fact, I'm not going to go through the derivation of this equation. It's a lot of math. We're just going to use this equation. That's fine. This level. Let's use it. Let me see if my email came through. Here it is. I used 2 methods to solve problem 89, which is simultaneous with 2 equilibria. The 2 equilibria was HCN and KW. So I had Ka and KW I had to solve simultaneously. So this is the setup I did before in class, where we start off with Y hydronium from water, and we add X hydronium from HCN, and we get Y plus X. And over here for water, we start off with X hydronium from HCN here, and we add Y, and so we get X plus Y. Well, X plus Y and Y plus X are the same. And so that's simultaneous. They come up with the same solution. And so we come up with 2 equations. We come up with the expression from equilibrium 1, HCN, Ka and Kw. Normally when we have 2 equations and 2 unknowns, what do we do? Ci is known. 2 equations and 2 unknowns, we solve for y or we solve for x. So this is trick number 1. You don't solve for y, you don't solve for x. If you try to solve this for y or try to solve it for x, you're in for a headache, right? It's not going to work. And so what we do is we solve it for y plus x. If you solve it for y plus x, then we get this, and then we substitute this in the other equation. And so that's trick number 1. So we do some substitution and we end up with generating this equation. And then we go through this equation here, like this. And then eventually we come up with an X value. But in order to get this X value, this turns out to be actually quadratic. Yeah, this ends up being a quadratic. However, what we do is we use the simplifying assumption here. Otherwise, this becomes very difficult to solve. And so this is using the simplifying assumption, and here I'm justifying the simplifying assumption here. However, that's what the book suggests. Or no, the book suggests to use method of successive approximations. So instead of using the simplifying assumption, was it justified? It was justified, but we can improve this by using the method of successive approximations here. And we can go through and do that, and then eventually I get some numbers here and some more numbers here. And here I've showed the method of successive approximations. So you have to definitely do some tricks to solve this. It's not a simple 2 equation, 2 unknown problem. And then continue on here, and then we go down here. And so I showed the difference here. With the simplifying assumption, without the simplifying assumption, it came out a little bit different. This is with successive approximations. I'm sorry. Without successive approximations, the simplifying assumption, it came out a little bit different. So successive approximations, we expect to be a more accurate answer, as long as I zoom in on that target and get this pH 6.90. So for some people, this might be a little easier than generating a whole bunch of equations and the mass balance, charge balance thing we did earlier, or I showed you earlier. Okay. But I'll post these in case you're interested in it. But somebody else did all that, and they come up with this. And sometimes that's what you do. You don't come up with the answer being a specific number. You come up with the answer as being an equation. And you can use that equation to generate the answer. That's actually more useful for a lot of problems, to come up with an equation rather than a specific answer. Because if you have an equation, then oftentimes what we do with an equation is we look at the range of values. So if you calculate, okay, how many grams am I going to get? You're going to get this many grams, let's say. You start off with this. So it's always like you start off with X grams of A, Y grams of B. How many grams of Z are you going to get? You're going to get whatever. Versus an equation. When you have an equation, then you can see the limits of the equation. The equation can't go beyond this and this. So what you can say is, at the low end of the spectrum, you'll get this. At the high end of the spectrum, you'll get that. And so when we solve problems with an equation, sometimes it's more useful because we can visualize the whole spectrum rather than one color. If you look at the rainbow and you're only looking at this shade of green, and that's all you see is that shade of green, you don't know the whole rainbow, do you? How big is that rainbow? But if you solve it for an equation, then you might see the whole rainbow because you can easily look at the limits of the equation. Does that make sense? So in science, we often solve problems not for a single answer, but for an equation. Well, this is one of those things. We solve this simultaneously, we get this equation, then we can use that equation to do different things. This is the same thing for quantum numbers. When we solve the Schrodinger equation, we end up with a whole bunch of equations, and those equations dictate the quantum numbers of the solutions to the wave functions, for the Schrodinger equation. All right, going back to this, so for amphoteric it's a bit more complex, but let me talk about other types of salts since we're on this topic. Since we're on this topic, I'm going to diverge a little bit. Although I didn't quite finish phosphoric acid, did I? Actually, I'd like to finish phosphoric acid before I move on here. We got to what, step 3 for phosphoric acid? Did we do KW? We did KW? Oh, okay, this must have crashed or something. Because I just saw this. Okay, then we're done with that. So what I want to talk about here next is this. In Chem 1A, the way, we had it, we have an articulation agreement with the UCs, so we're supposed to cover certain topics in Chem 1A and certain topics in Chem 1B, and that means that sometimes we have to split chapters. But some instructors don't like to split chapters. So we're supposed to cover sections, the last 3 sections of chapter 17 were supposed to be covered in Chem 1A. Did you guys cover those in Chem 1A? Structure and acid strength and base strength. I mean, I covered them in Chem 1A, so this is going to be a repeat of that for this. So the first thing I want to talk about are salts. So we have different kinds of salts. We have neutral salts. Neutral salts, examples of neutral salt would be sodium chloride. Chloride's a base, but chloride is what we call the conjugate base, CB, conjugate base of hydrochloric acid. And the Ka for hydrochloric acid is very large. Therefore, the Kb for chloride is very small. There's no number for this. It's so small, we call it negligible. And if it's negligible, we think of chloride as being neutral. So let's say you ran out of antacid, but you have lots of table salt. Could you use the table salt instead? Let's say you have a little too much acid in your stomach. You want to neutralize that. And you don't want to run to the pharmacy to get some more antacid or the grocery store. Can you just grab a bottle of salt and start chugging the salt down to help neutralize your stomach acid? Is it going to be very effective? No, and so we know that chloride is totally ineffective. So what we say is sodium chloride is a neutral salt. You should have gotten a pH of 7. However, you might not have gotten a pH of 7 because CO2 contamination of it will probably drop the pH below 7. And so it's supposed to be pH 7. Potassium nitrate, potassium ions, they're not acidic or basic. But nitrate's the conjugate base of nitric acid. That means Kb is very small, negligible, and therefore we say it's pH neutral. The pH should be 7. Yeah. So we have neutral salts. We have acidic salts. Example would be ammonium chloride. Ammonium has a decent Ka. What is the Ka for ammonium? 5.7 times 10 to the minus 10. Not very good, but not, terrible. This is weak acid. This is acidic salt. Let me give you another example of an acidic salt. FeCl3 is another example of an acidic salt. And why is FeCl3 an acidic salt? And so let me talk about that now. I just need to add some pages to this. I forgot to do that.
I had a question. So how you said ammonium chloride is an acidic salt, but we just talked about chloride ions being a conjugate base.
Mm-hmm.
How does that?
We completely ignore chloride. So chloride's neutral, and therefore ammonium is acid, so we call it an acidic salt. Completely ignore the chloride. Well, I need to backtrack one step. Here. You know that super simple, well, actually, let me continue here. FeCl3 aqueous consists of Fe3 plus aqueous and chlorides. Chlorides we just completely ignore, and so let's focus on Fe3 plus aqueous. Fe3 plus aqueous turns out to be a decent Lewis acid. So what we end up forming is this. We end up forming a complex. And so we'll have 6 waters that will bind to the iron 3 plus, and we'll form this. What's this called? Hexaaqua, not ferrite. Hexaaqua iron 3. So if you read this chart, you'd see that hexaaqua iron 3 is here, which means hexaaqua iron 3 is a stronger acid than, what's this one called down here? HNO2. Nitrous acid? Good. It's a stronger acid than nitrous acid, but a weaker acid than phosphoric acid. Phosphoric acid is one of the stronger weak acids. And therefore, it's a pretty decent acid. This is for sure stronger than, do you know what this one's called? HCOOH? Acetic acid is CH3COOH. So acetic acid is right below it. This is acetic acid. This is called formic acid. Formic acid. Ants use formic acid for their defense. It's well above acetic acid. Right? It's a pretty decent acid. What makes it a good acid? Well, it's a good acid based on its ranking in the chart, but what makes it a good acid is this. What makes it a good acid is, normally we do something weird with complexes. What we do that's weird with complexes is we don't really look at the bonding here, but we really should look at the bonding. But the bonding is described by MO theory the best. And so that's why we kind of ignore it. So when we look at the complex like this, the waters are treated as neutral, and the iron is treated as +3. And so we leave it like this. But really, when we look at the waters, what's happening with the water is they're forming a coordinate covalent bond with the iron here. And so if I attach one water on here, like this, then what that's going to do is it's going to change the formal charge on oxygen. It's not going to behave like water. Water is like this. And the formal charge on oxygen and water is 0. However, what would the formal charge here be? Not negative. It would be +1. The formal charge on this, the +1, where have you seen that before? You know where I've seen that before. I've seen that here. This reminds me of this. What is this called? Hydronium. So when I look at this water, that's kind of hydronium-like to me. This looks like acid, doesn't it? But again, we don't do this with complexes. Complexes, we leave the water as neutral and the iron 3, because iron 3 should have gone to iron 2, and this should be +1. That's what should have happened, right? If we were using valence bond theory. But we don't, so we leave it. But what results is a very acidic hydrogen. A very acidic hydrogen, in other words, if I look at the delta, if I look at this hydrogen here, let's say, and I look at what we call delta plus, this is a polar bond here. And this bond is going to be polar because oxygen is more electronegative than hydrogen. So oxygen is going to take most of the electron cloud away from hydrogen. Oxygen's electronegativity is a 3.5, right? But is this oxygen the same as this oxygen here? No, because this oxygen is not the same at all, because this oxygen has a positive charge. And so let's look at some examples. When we look at electronegativity, we have to look at not the element, we have to look at the element and its electronic environment. So what is the electronegativity of fluorine? The electronegativity of fluorine is a 4.0. But if we have fluoride, is the electronegativity of fluoride also 4.0? No. In fact, fluoride doesn't want another electron. You would think fluoride wants another electron to go 2 minus, and another to go 3 minus, and another to go 4 minus. Why doesn't it stop? If fluorine's the most electronegative, you would think it is it being the most greedy. If it's the most greedy, then it should take as many electrons as it possibly, as it possibly can take. Why doesn't it? Yeah, now it has an octet, and so any extra electrons are going to go into the third shell. Well, that's not going to happen. And so that means the electronegativity of fluorine is not, fluoride is not 4.0. It's much less than 4.0, correct? So when we do electronegativities, we have to take that into consideration. This is a neutral oxygen. This is 3.5, but this one is a positive oxygen. So the electronegativity of this oxygen is going to be much higher than 3.5. Right? Just like if I had fluorine with a positive charge. If I put a fluorine with a positive charge, then is it also going to be a 4.0? No, it's going to be much greater than a 4.0. And so that's going to change the bonding environment, and then this is going to have a much larger delta plus. Now, if you're a base, there are different bases. Like one of the best bases around is hydroxide. If you're a hydroxide, what are you looking for? If you're a hydroxide, you're looking for a proton. A proton, the best would be H+. That would be the best. It has a full positive charge. But if you can't find an H+, then you're going to look for the next best. What would the next best be? The one that's most proton-like. And so between these two hydrogens, which one's more proton-like? The one with the iron is the most proton-like. And so the easiest way we're going to visualize this is this. Do you guys remember the electrostatic potential maps? What color is positive? Normally I always think of red as being positive, but in an electrostatic potential map, it's not red. What color is it? It's blue. So proton, this is great because this is going to be a little concentrated blue dot here. This. But when we compare these two hydrogens, they're going to have different levels of blue. Like this hydrogen is going to be more blue, more positive than this hydrogen here. I should have put the electron cloud with a different color. And so if you're a hydroxide, you're looking for the most blue because hydroxide, what color is hydroxide? Red. And so red wants blue. So if red wants blue, which one is going to be the most blue? It's going to be the proton. But if you don't have a proton, then you're going to pick the most blue one, which will be this. And so this is unusually acidic water molecules because of the bonding environment there. And so this is why hexaaqua iron 3 is a pretty decent acid. It's a pretty good acid. Now, the waters, some waters are easy to break off, some are stuck on there. These waters can break off and reattach and that kind of stuff. We call that labile and inert. Labile means they're easy to break off. Inert means they're hard to break off. So it depends. So what we can say is that the more blue the hydrogen is, the more acidic it should be. So does it make sense why iron, the hexaaqua iron? Yeah, okay, good. But then, if you go through these charts and you look at these, and you start to notice things that you might not have noticed, in the past. And these things that you notice, there's usually not enough time to talk about all of them, but if we do HI versus HBr versus HCl, which of these three hydrogens is the most blue? HI is the most blue because iodine is the most electronegative, and so it's going to suck more of the electron cloud away from it. Is that it? What creates it to be more blue is just the polarization of the electron cloud. And so iodine is most electronegative, so it's going to suck the electron cloud towards it, leaving hydrogen bluer and bluer, and iodine redder and redder. Does that make sense? Is that correct? Or does that seem wrong? Because if I think about it, is iodine, which one of these is more electronegative? Chlorine, bromine, or iodine? Chlorine. Chlorine's more electronegative. So if it's more electronegative, then that means that the HCl bond is going to be more polar than the HI bond. If the HCl bond is more polar, then that means that hydrogen is bluer. This hydrogen is a deeper blue than that hydrogen. Right?
Yeah.
And I just said the more blue it is, the better the acid because the more proton-like it is. So this one's going to be the most proton-like. Proton-like is a full positive charge. So the higher we can get to a full positive charge, the better. And so this is going to be the most blue. Therefore, HCl should be the strongest acid. Therefore, this chart is wrong. Right? They need to fix the chart. It turns out that this chart is derived from experimental data, and we need repetition, and there was a repetition, and indeed it turns out HI is a stronger acid. HI is a stronger acid, then my hypothesis is just, might as well toss it into the trash, right? Should I? Well, it turns out there are other factors in addition to how blue the hydrogen is. Definitely having it more blue is this, and so this is what's going on with this. What's going on with this is if you're a base, you're definitely going to want this hydrogen. You're going to want this hydrogen, but in order to get this hydrogen, you have to take it away from chloride. And this hydrogen doesn't look as appealing. But this hydrogen, if you want this hydrogen, you have to take it away from iodide. And it turns out that chloride doesn't want to give up that hydrogen as easily as iodide. Iodide gives up that hydrogen a lot easier. Why is that? Yeah, the bond is a lot weaker because iodine is a lot bigger. And so when we look at the bonding here, and when we look at the bonding here, the HCl bond would be an s-sp3 sigma bond. And the sp3 orbitals are going to be made of the 3s and the 3p hybridized orbitals here. Whereas if we look at iodine, and hybridization is a result of VSEPR, valence shell electron pair repulsions. The bigger the atom, the less repulsions we're going to get, because there's more space available. And so this might not be hybridized, but I'm just going to treat it as hybridized as well. And so that's going to involve using much larger orbitals. It's a fifth period, 1, 2, 3, 4, 5. Fifth period versus third period. Fifth period, the 5s and the 5p orbitals are huge, aren't they? Compared to the 3s and the 3p orbitals. And so basically, it's this. We're going to get this poor orbital overlap when we look at this here. So if we look at the s orbital on hydrogen versus the sp3 orbital on chlorine, we get good orbital overlap like this. This is chlorine, this would be hydrogen here. Versus when we look at the hydrogen s orbital and the p or the sp3, depending if you want to hybridize it or not. And again, it may not be hybridized because there's less repulsions here. But I'm going to hybridize it. This is iodine. We're going to get a weaker bond. We're going to have more negative charge concentrated here from the electron cloud, and the nuclei are going to be attracted to that more strongly. And the electron cloud here is going to be quite dispersed over a large volume. Therefore, the nuclei, which are positively charged, aren't going to be as strongly attracted to this cloud as they are. And so, in other words, we're going to get more concentrated negative charge density here, and then less concentrated negative charge density here, resulting in a weak bond. And so this is a pretty weak bond. And this turns out to be a stronger bond. And so the hypothesis is modified a little bit to incorporate this here. And so for sure the base is going to be more attracted to HCl. But the problem is it's just going to have a hard time plucking it off compared to HI. The base is going to be less attracted to HI, but it's going to be a lot easier to pluck off. Does that make sense? And therefore HI is a stronger acid. And so when we think about acid strength, there are even more factors that affect acid strength. And so now I'm going to discuss the factors that influence acid strength as well as base strength. What's more important, how blue it is or how strong the bond is? How strong the bond is. And so the number one factor that we look at is the HX bond strength. HX bond strength. Number one. Number two, if let's say the bonds are the same, it's an HO bond. Then what we look at is the bond polarity. In other words, the more blue, we expect the stronger the acid. The more, what's the opposite of blue here? Well, not really. Let's go with this. Let's compare this species with this species here. Let's see, what should I do here? Are these hydrogens very blue? No. Do you know what color these hydrogens would be in the electrostatic potential map? These would be green. Are bases attracted to green hydrogens? No. Bases aren't. It's like, you know, some people like green bananas, you know. I think. No? Some people might eat green bananas. If there are no other bananas present, would you eat a green banana? No?
Depends how green they are.
In some cultures, they do put plantain as part of soups.
Oh, okay. All right. Well, let's say you're unusually hungry. You're super base. Would you attack it? Yeah, if you're a super base, you'd attack it, and you'd form what? You'd form, if you're a super base and you attack this, you'd form methide. But most people stay away from green hydrogens. And so, however, this one is looking pretty good. This hydrogen here looks pretty good because this would be fairly blue, right? That's looking good. What about this hydrogen over here on the left side? Should I ignore that hydrogen or should I factor that hydrogen in? No, this hydrogen is going to be more green. So that hydrogen doesn't look as appetizing unless you are super hungry. Let's say you haven't eaten in a long time. You know? And I'll tell you, the eaglets are really hungry. They're eating all the time. It's pretty interesting watching them feed. And Big Bear has a lot of fish and other birds. They feed the eaglets. But anyway, if there was very little food, then yeah, you're going to be plucking these green ones off. You know, if you're strong enough. You might not be strong enough. And most aren't, but the blue one will be okay. All right, so that's bond polarity. The carbon, let me tell you, the carbon-hydrogen bond and the oxygen-hydrogen bond are roughly around the same. You know what the covalent bond energies range from? Covalent bond energies range from on the low end, which would be like a peroxide bond, to the high end, which would be like a nitrogen bond. Do you know roughly the numbers? On the low end, it's about 100 kilojoules per mole. On the high end, it's about 1,000 kilojoules per mole. So nitrogen-nitrogen bond, which is a triple bond, is called a pseudo-inert bond. In other words, the reason it's pseudo-inert, it's called a pseudo-Nobel gas. Maybe not pseudo-inert is the proper word. Pseudo-inert gas. Or pseudo, now they don't call them inert anymore because eventually if you find something starving enough, it could react. You know, and rather than saying it's inert, that it can't react with anything, you might say that methane's inert, you know, in acid-base chemistry, but it's not really, because if you had something that's desperate enough, it could take that hydrogen in acid-base, you know. We don't usually think, you know, we don't think of this as an acid at all, but potentially could react. And so this is why they call them Nobel gases rather than inert gases. When I was going through chemistry, we called them inert gases. And it turned out the inert gases can actually react. Inert gases. And then eventually they changed it to Nobel gases.
So different than the Nobel gases.
No, all the Nobel gases used to be called inert gases.
Oh,
All
I
these
see.
gases used to be called inert, but
Gotcha.
inert means they're totally unreactive, but it turns out they aren't totally unreactive. And so they decided at some point to change it. When I learned these gases, they were all called the inert gases, and then eventually somebody said, no, that's not good. We should call them the Nobel gases instead. Yeah.
The bond strength range was from
100 to 1,000 kilojoules per mole. Just remember that. And then that's for triple bond. Triple bond's 1,000. And so if you got a decent single bonds are in the range of 300 to 400 kilojoules per mole. And so when we look at the carbon hydrogen and the oxygen hydrogen, they're in the 300 to 400 kilojoule per mole range. So there's not a huge difference in the bond strength. And so we're looking at the bond polarity here, or the blue. Okay, so we look at that. So these are the two factors that we have so far, and let's take a look at our data table again. We look at our data table here, and I have, this makes sense. HBr is going to have the weakest bond. Oh no, HBr is not the weakest. HI is the weakest, followed by HBr, followed by HCl. And so based on bond strength, HI is predicted to be the strongest. But based on polarity, you know how blue the hydrogen is, based on polarity, which one should be the strongest? HCl. But is Cl the most electronegative element on the periodic table? No, Cl's not. What is the most electronegative element on the periodic table? Fluorine. And where's fluorine? HF is down here. Why isn't HF with the rest of the family? Yeah, there's a huge drop here in terms of strength. HF is 1 million times weaker than HCl. 1 million times weaker. So, so that's easy. If we factor in these two, then we see that HF is 10 to the 6 times weaker than HCl. It's going to be the bluest. It's going to be the bluest of all the hydrogens. because it's the most polar. And so if you're a base, you're going to be attracted to this hydrogen the most, right? Because it's the bluest. The problem is breaking that hydrogen off. Fluorine's going to give quite a fight for that compared to chlorine, let's say. Actually, all of them eventually will lose. I mean, somewhat. But it doesn't. And so if it's 10 to the 6 times weaker, then that means it has to have a million times stronger bond.
So if you have a solution of like hydrofluoric acid and also hydrofluoric acid or some other, one of those, will it like slow down the base because they're more attracted to the
Yeah,
the
yeah.
hydrogen and
But
hydrofluoric?
when you look at how fast they're moving, it slows down is like, if you put something in there that, it would slow it down. It could potentially slow things down. But these reactions happen so fast, these acid-base reactions, that slowing down is okay. If you slow down from, let's say, 65 to 64 miles an hour, you slow down, but it's not really going to be impacting things much, that kind of thing. However, that's a strategy that people use. They put in inhibitors. So let's say you don't want a reaction to occur, so you put a competing compound in there, and that inhibits the other reaction, so it really slows it down. So there's a much more favorable reaction. The problem with this is this isn't a favorable reaction. This is a less favorable reaction. And so the HF comes in there, but nothing's going to happen because, it's a million times weaker. And so not much reaction occurs. If you put something in there that's even more favorable, let's say HCl, and you throw in some HI in there, then everybody's going to be taking the proton off HI, and the HCl is going to be completely ignored. There you're going to see a huge slowdown in the HCl. But anyway, getting back to this, so my question is if it's 10 to the 6, so let's say it's a bond, a single covalent bond is like 300 to 400 kilojoules per mole. And so does that mean an HF bond must be 300 million kilojoules per mole to 400 million kilojoules per mole? Because it's a million times weaker, and therefore it must have a million times stronger bond? Does that even make sense to have a million kilojoules per mole bond energy? It makes absolutely no sense. So the bond energy does not explain this, and the polarity doesn't explain this. So what else is there? Well, like I said, there are multiple factors, and so we have to continue on with this. Otherwise, our hypothesis has failed again. So number 1 and number 2 don't work for HF. And so we go on to number 3. Number 3 is the stability of the conjugate base. In other words, the stability of product. Which is the conjugate base in this case. So when we do the stability of the product, the conjugate base, what's the conjugate base of HI? The conjugate base of HI is iodide. And then the conjugate base of HBr is bromide and chloride and fluoride. And so we see that all these are negative, negatively charged, -1. However, when we're looking at bases, we don't look for blue. Acids are blue, bases are going to be red. Are all these going to be the same? No, they're going to be different. In fact, for fluoride, the red is going to be concentrated here. Whereas for iodide, the red is going to be more diluted. It's going to be more diffuse here. And so what I call this is, I call this charge density. And charge density is which one is going to be more reactive, which one's going to be less reactive. Charge density. More reactive. This is more reactive. More reactive means less stable. Less stable. And this is going to be less reactive, which means more stable. So does that mean that fluoride's like 1,000,000 times smaller than iodide? Or the iodide's 1,000,000 times bigger? Is that what it means? No, not even close, because atoms range in size from, do you know what atoms range in size from?
100 to 600.
About 100 to 600 picometers, and then anions, you double that, so maybe 1,200. Cations, you shrink that in half, so the range is a little bit wider, but not 1,000,000 times wider, right? So this isn't it either. Although iodide is more stable, so that kind of makes sense, HI. And so this is a stability product. This is number 3. So number 3 doesn't work for understanding this. So we're going to go to number 4. While I'm on number 3, I might as well talk about a couple of things here. We're going to talk about charge, localization versus delocalization. And let me give you a couple of examples of charge localization versus delocalization. If we look at hydroxide, versus formate. Both of these have a negative charge on oxygen, so are they equal in base strength? In other words, are these equally red? You got a negative charge on this oxygen, you got a negative charge on this oxygen. Shouldn't they be equally as red? And it turns out they aren't. Which one is more red? Hydroxide's more red. Why is hydroxide more red than, this is called formate ion, than formate? Yeah, because when we think about delocalization, there are two things we look at. Number one, we look for resonance delocalization. And number two, we look at the inductive effect. Inductive, we look at both electron withdrawers. Typically, when we look at the electron inductive effect, we just look at electron withdrawers. But we also have to look at electron pushers. Electron pushers and withdrawers. And so the impact here, the main impact is resonance delocalization. Resonance delocalization is we can generate another resonance form for this here, for formate. And we end up with this. The true, or the most accurate structure will be a resonance hybrid. And so the hybrid structure is going to be an average of those two. The average of those two is going to have the pi bonding electrons spread out over both. So this is what you're mentioning. And the formal charge. The formal charge is going to go from -1 and 0 to -1/2 on both. This is called resonance delocalization. So this is called localized charge here. And this is delocalized charge. There's also an inductive effect here. In the inductive effect, you'd expect this. Carbon versus hydrogen. Which one's more electronegative? Hydrogen is a 2.1, carbon is a 2.5. So carbon's more electronegative. So carbon is going to have an effect of withdrawing more of the electron cloud than hydrogen does up there, because it's more electronegative. But electronegativities, we have to be careful because we should also look at the formal charges and the oxidation states in order to properly do that. And so the primary effect here is resonance delocalization. Now, let's compare that with this. This is called methoxide. So if we look at methoxide, let's look at methoxide versus hydroxide. If we look at methoxide versus hydroxide, we'd say, carbon here versus hydrogen here attached to the oxygen. And you say carbon's more electronegative, so it being more electronegative is going to suck more of the electron cloud towards it, right? If it sucks more of the electron cloud towards it, it makes this oxygen less negative. Whereas this hydrogen doesn't suck as much of the electron cloud towards it, and so it stays quite negative here, right? Does that make sense? However, we have to look because electronegativities, the Pauling electronegativities are oversimplification of our world. We don't want to oversimplify things too much, because if we oversimplify things too much, then we always call fluorine 4.0 for everything. Fluoride, fluorine plus. When we compare these two carbons, are these two carbons similar in terms of electron rich or electron poor? And so if I compare this carbon versus this carbon, I see a dramatic difference. When I look at this carbon, I say that carbon's electron poor. When I look at this carbon, I say this carbon's electron rich. That's going to impact its electronegativity. If you have an electron rich carbon, it isn't going to be as electronegative as an electron poor carbon. Electron poor carbon is going to be more electronegative. Electron rich carbon is going to be less electronegative. And so why do I call this one electron rich and this one electron poor? Well, we talked about electron rich and electron poor before, and how do you determine what's electron rich and electron poor? Oxidation state. So when we look at the oxidation state, what is the oxidation state of this carbon here? The oxidation state on this carbon is minus 3. It kind of looks like -3 because it's methyl. Methyl is normally a -3 oxidation state, but methyl is usually bonded to what we call an R group. R group is either carbon or hydrogen. So when we look at the methyl group, but this is a little bit different. It's winner take all, so it's going to be 2, 4, 6, and then gets none of these. Whereas in methyl, it usually takes half of those because it's bonded to a carbon or hydrogen or something like that. And so, or usually bonded to carbon. And so in this case, we only have 2, 4, 6. It's supposed to have 4. That means it only has 2 extra electrons. If it has 2 extra electrons, it's minus 2 oxidation state. This is a +1 oxidation state here. So what we say is that a methyl group here, this is electron rich, therefore we call it electron pusher. If it's electron rich, it's electron pusher. If it's electron pusher, it's pushing negative density out this way. If it's pushing negative charge density out this way, it's going to make this oxygen more blue or more red? More red, right? More red. And therefore, if I put an electron pusher group here, that's going to make this one more basic. And so what that means is this. It means that formate versus hydroxide, hydroxide's stronger. Methoxide versus hydroxide, methoxide's stronger. Methoxide is a strong base, but there's one, number 4, which we'll get to on Monday. I did throw in some problems, acid-base strength problems. You can look at those, but I'll put those as bonus since I didn't quite get there. I'll talk about it on Monday more. I'll finish acid-base strength then. Test is on Wednesdays. Test is still going to be on Wednesday, even though I didn't quite finish.
And these are due Monday?
The quiz is due Monday, but I'll talk about it. You can turn it in at the end of Monday. I'm going to talk about acid-base strength a little bit more on Monday. If you're confused about the acid-base strength ones, try them and see if you can figure out which one's a stronger acid, which one's a stronger base.